Okay, let's talk about this. On this first one, what the heck is going on? On this first one, the pattern that we have here, looking at it, first of all, is in terms of signs, it's positive, negative, right? And so to create that, I'm going to need to use a -1, but I need my first one to be positive, so n plus 1. All right, now the numerators looks like it's what, 5, 7, 9 would be nice. 11, 5, 7, 9, 11 would be nice. It looks like they're odds, but I don't have a 9 there. The bottoms look like what? 3, 9. Those look like possibly powers of 3. So maybe if you squint your eyes hard enough, you'll see 5, -7, 9, -11. Oops. And then on the bottom, it would be 3, 9. The next one should be 27, then 81. And look, 9 over 27 is 1/3. Right? So how do I create the odd numbers on top, starting with 5? 2n plus 3. And then the bottom, just powers of 3, starting with n, 3 to the first power, so just n. That would work. Okay? All right, now this one. Does this sequence converge or diverge? Well, if I take a limit as n goes to infinity of n squared over n factorial, these both become infinite. So I have like an infinity over infinity. But you cannot use L'Hopital's rule because you have a factorial, and factorials, I told you, you can't use L'Hopital's rule when you have factorials. So one thing we could do here is use like a squeeze theorem to try and squeeze this down. But let's first write down what is n squared over n factorial. It's n times n, right, over n times n minus 1 times n minus 2, all the way till I get down to what? 1? That's what it is. I'd like to know if I can get some control over this, if I can put this between two things and then show that those two things go converge down. So n over n, those two will cancel, right? Those are gone. So I'm really just looking at n over n minus 1, then n minus 2, and this keeps going until I get down to 1. Can you give me something that this is between? So let's start with this. What is this definitely greater than? 0, right? It's bigger than 0 because it's a positive number. And then, what can you tell me about this number right here? Is it bigger than 1, smaller than 1? It's a little bit bigger than 1, right? Like if n was 5, that would be 5 over 4, something like that, right? Okay, so I know that that's a little bit bigger than 1. I know that. But what about the next number? We can imagine that being like a 1 over that times 1 over the next one. What's 1 over n minus 2? Is that going to be smaller than 1 or bigger than 1? Smaller than 1, right? The next one, smaller than 1. The next one, smaller than 1. So what I'm trying to get you to see is that all of this junk down here together, all of it, not this one, everything down there is a number smaller than 1 times a number smaller than 1 times a number smaller than 1, right? So that whole thing should be smaller than 1. Agreed? So if I take this right here, which I said was already bigger than 1, and I multiply it times something smaller than 1, do you agree that that's less than or equal to that? Do you agree with that? Yes? Because if all this junk right here is smaller than 1, multiplying it times this would make it smaller than just that, right? Okay? Now, but there's a problem here. If I try and use the squeeze theorem now, what happens is n goes to infinity here and here. This goes to what? What does this go to if n goes to infinity here? Infinity over infinity. Can I use L'Hopital on this? Yes. What would that give you? 1. And then what's it bigger than? 0. So I'm trying to squeeze it between 0 and 1. That's not good enough. They have to go to the same place. So tell me if you agree with this. Is this still true? This right here, we said this was smaller than 1, but if I peel these two off together, these two times the rest of it should be smaller than these two just by themselves. Now, this one here goes where? To 0, because you have n on top, and then on the bottom you have like a quadratic, n squared. And if you did L'Hopital on that, that would go to what? It would go to 0, wouldn't it? So what will happen by squeeze theorem is that this goes to 0. This, if I take the limit as n goes to infinity, will also go to 0. And so we have squeezed this thing between the two. So it goes to 0. Okay, I'll count that one as a bonus, all right? If anyone got that one. Anybody get that one? I mean, not that the answer was 0, but did anyone justify the work? There was one similar to that in the homework. So, okay. I said I would address questions, but I can only answer maybe 1 or 2 questions from homework. So, I know we had number, what, 30, what was it, 40? Was it 40? Where's my book? What was it? What was the a sub n? N minus? N plus 1 over n. Okay. So the instructions on this were to, what? See if it's increasing or decreasing, right? Is it increasing or decreasing? And then what? And it's bounded. Determine if it's increasing or decreasing, determine if it's bounded. So I'm going to start by writing out some of these first pieces to this. Plug in 1, what do you get? 1 plus 1, you get 2. Plug in 2, you get 2 plus a half. 2 and a half, which is really 5 halves. And the next one would be 3 plus a third, which would be 3 and a third, which is 10 thirds. Right, we're not writing this anymore, right? This is what we did in grade school. This is what we do in calculus, right? 3 and a third is 10 thirds. I'm just telling you that because, I mean, did I tell you about that toilet paper on the foot thing? No? Well, I'm just saying it's like writing this in a Cal 2 class is like walking around with toilet paper on your foot. You know? It's kind of like, ooh, look at that guy. That's writing this sort of thing is kind. I mean, you should know it's there, but mixed numbers are just not used in higher level math. They're just not used. Right? Like if I want to write 5 halves x squared and I want to take the derivative, right? Then I bring the 2 out and I multiply, it hits the 5, I become 10 halves, right? Something like that. You never would write 2 and a half x squared, take the derivative, right? You would never do that. Because you might think that means 2 times 1 half, right? You might think that. It's not 2 and a half, or 3, let's go back to this one. 3 and a third, the reason why this is bad notation is because it really means 3 plus a third. And people forget that that's what it means. So, make that go away. All right, 10 thirds. And then what's the next one? So 4 plus a fourth, 17 fourths, and then this keeps going, right? Now, what does it look like it's doing in terms of increasing, decreasing? Looks like it's increasing, right? This is 2, this is 2.5, this is 3.333, this is 4 point something. So it looks like it's getting bigger. So I'm going to go for increasing, all right? I want to show a sub n is increasing. How do I show this? So I want to show that a sub n is less than a sub n plus 1, right? That's what it means to be increasing. What would a sub n be? Well, it's defined to be n plus 1 over n. Is that less than what's a sub n plus 1? So you're rewriting the original sequence, but replacing n with n plus 1. So it's n plus 1 plus 1 over n plus 1. And now what I need to do is take that expression and somehow at the end of it, convince you that it's always true. And remembering that n here for us is always going to be 1, 2, 3, 4, 5, 6, always a positive integer starting with 1. What can I do first? Subtract n on both sides. That has no effect on the inequality, right? Because it's subtraction, not division. What else? Anything else? Here's where I am, right? Okay, at this point, you're free to do whatever you want. I'd like to get the n's out of the denominators, right? So I think to do this, I'm going to have to multiply both sides of this inequality by the common denominator, which would be what? N times n plus 1. So I'm multiplying n times n plus 1 here on this side, and I'm going to take this whole side and multiply by n times n plus 1. Now, do I need to worry about flipping the inequality? Because I am multiplying both sides of an inequality by something here. No, why not? N is always positive, so I don't have to worry about that. Okay, so when I multiply on the left side, what do I get? N plus 1. Less than. Over here, I have to distribute this to the 1 first, which gives me n squared plus n. I'm going to go ahead and just multiply n times n plus 1. Then I distribute here to here, and I get what? Plus n. You all still good there? I can cancel one n from each side. I think I'm convinced at this point. N has to be at the least 1, right? So at the smallest, this would be 1 plus 1, which would be 2, which would be greater than 1. Any other n I plug in is just going to get bigger, right? So I'm happy with that. You could also have looked at it like this, n times n plus 1. If the smallest this could be is 1 and the smallest this could be is 2, then those two multiplied have to be bigger than 1, right? Okay. So I've shown it's increasing, sorry. The next thing I need to show is whether or not it is bounded. Bounded, right? It doesn't say bounded above or below, right? Is it bounded? Well, do you agree with this? Do you agree with that? Yes, this is a positive number. This is a positive number. This is definitely true, right? You add two positive numbers is bigger than 0. So that tells me for sure it's bounded below, right? But is it bounded above? Right? Is it bounded above? Well, what I'll do is I'll just take the limit. What's the limit as n goes to infinity of n times 1 over n? Infinity plus 0. And what's infinity plus 0? Infinity. Which means that this thing becomes infinitely large, which means there is no upper bound. It doesn't go to negative infinity though. The n goes to 1, yeah. But you wouldn't say let n go to 1 because bounded below what it does in the beginning doesn't really necessarily matter. It could take off and start going down, right? So no upper bound. Not bounded then. For now, yes. for now. We still have to address it could be 0. It's not negative normally, no. Yeah. It would be wrong for me to say it can't ever be, okay? Because it's what we call an index, and we can use our index however we want. The standard is 1 and 0. That's right. That's pretty much. And in fact, a lot of times it can be confusing because sometimes people will write like a summation, and they'll just write the expression here, n over n plus 1, and they're not telling you where that sum starts. They're assuming it starts at either 1 or 0. And sometimes you don't know which one it is, so it can be a little bit tricky. But okay, we have to continue to move on, so I'm going to start 8.2. Series. So we'll start with the definition. A series, or sometimes called an infinite series, is just the sum of the terms of a sequence. That's it. That's all a series is. You take a sequence, which is a list of numbers, and you add them up. If your sequence is finite, then your series is finite. If your sequence is infinite, then your series is infinite. So in other words, i.e., if a sub n is given, a sub 1, a sub 2, a sub 3, let's say it's an infinite sequence, right? So that's a sequence, right? This is a sequence. So if you're given a sequence, then the series is A1 plus A2 plus A3 forever. But we don't like to use this notation. We like to use a more condensed notation. So we bring in the Greek capital letter S, sigma. So this, by definition, is equal to sigma n equals 1 to infinity of a sub n. Or you could write sum k equals 1 to infinity of a sub k. Or you could write sum j equals 1 to infinity a sub j. Or any index variable you want to use. All right? These are called dummy indexes, dummy variables. All it does is tells you what's being replaced. I'm going to start, now we did sigmas when we were doing Riemann sums, right? So I'm assuming you remember that. This just means add up stuff, start with n as 1, stop, never stop, right? And all you do is you replace this n first with 1, and that would be a sub 1. Plus, then go to 2, plus, then 3, and that's what it would create, wouldn't it? But if I replace that n with k and replace that n with k, it's the same thing, right? Okay, so that's the notation. Another definition. This is what's called the nth partial sum. If a sub n equals a1, a2, a3, so we're given an infinite sequence, tell me what just taking the sum of the first term would be. Just be a sub 1, right? So I could define, if I want, s sub 1 to be equal to a sub 1. I could define s sub 2, s meaning sum, okay? Think of this s as like a sum. S sub 1 means just add up the first guy. S sub 2 would mean add up what? The first two guys. Oh, wait, one of them is a girl. So we want to be, I don't want to be gender biased here. All right? So add up the first two instead of the first one. What would S sub 3 be? Just add up the first three, right? And I could keep doing this, couldn't I? And I could actually come up with an S sub n, which would mean add up just the first n, right? But stop. Do you agree? I would stop. So let's make sure you're very clear on what's going on here. You're starting with a sequence, which is a list of numbers. That list of numbers could be anything. Then I'm actually generating a new sequence of numbers, aren't I? Based on that sequence. That sequence of numbers, S1, S2, S3, are the corresponding sums when you just take a partial sum. See, you're not going to add them all up, you're just doing part of them. S1, you just do the first one. S2 is the first two. S3 is the first three. Sn is the first n. So this right here, S sub n, is what's called the nth partial sum. Understand? Notice, please notice, that this S sub n created a new sequence, right? That's a new sequence. But it's not the same sequence as the one that was up here, right? It's a sequence of the sums. And guess what we want to know about this sequence? Does it converge or diverge? Right? Does it converge or diverge? Does this thing go to something? What if it does? What does it mean? What if I tell you that this sequence right here converges to 1? What does that actually mean? It means that this list of numbers, if you keep adding them forever, adds up to be a number, and specifically adds up to be 1. Not that each one of those is getting closer to 1, that when you add them all up, start throwing them into a pot, you start piling them all up, they add up to be a finite number of 1, if that makes any sense. Now, I'm going to get more into this, but I just want you to realize what we have here. No, it's not the same. Okay. So, before I get to an example, yes, that would be true. In fact, we'll have a theorem that says if the limit of the sequence does not go to 0, then the series diverges. Guaranteed. Okay, so this actually becomes, before we get into examples, I want you to think about this. When you're talking about an infinite series, adding up an infinite number of numbers, right? Is it possible to have a finite number? Is that possible? I mean, that's a huge thing that we have to get our heads around. So let's take an example of a sequence that we know. That's the sequence of integers, right? In fact, that's just a sub n equals n, right? If I said, start giving me the partial sums, what would the partial sums be? S1 would be just 1, and then S2 would be 1 plus 2, which would be 3, and then S sub 3, 3 would be 1 plus 2 plus 3, which would be 6, and I could keep going, right? Anybody know what S sub n would be? It's the nth partial sum is a finite sum. We stop at n, don't we? We stop at n. That means it's finite. I'm asking you to add up the first n numbers. How do you add up the first n numbers? No, that's multiplying the first n. This was something I gave us in class. There was a formula for it. You needed it for Riemann sums. I'm just seeing if anyone remembers it. Did I tell you about the guy who came up with a Gauss? But he didn't come up with it, but I told you a story about that, okay? So this would we actually have a formula for the nth partial sum for this particular sequence because we know that formula, like it's been given to us in the past, right? Now, it's obvious, I hope to you, that these are getting bigger. The first partial sum is 1, the next one's 3, the next one's 6. If I keep doing this, what would happen if I let n go to infinity? What would happen to this? It would be go to infinity, right? That makes sense that this sum, that this series, this infinite series should diverge, should go to infinity? Does that make sense that that would happen? These are going to infinity, and so is the sum. Perfectly fine. But what about something like this? How about I give you a sequence that, this time I'll just write it out. 1, 1/2, 1/4, 1/8, 1/16. Okay, that's a sub n. This is our a sub n. So let's look at the sums. What's S1? 1. What's S2? 1.5. I'm just kidding. 3/2. What's S3? 7/4. Right, that I'm getting by doing 1 plus 1/2 plus 1/4. Right? And I can keep doing this, right? My question here is this going to do the same thing the previous one did? You know, is these we know are what? This sequence up here, what's happening to this sequence? They're getting smaller and smaller and smaller. They're approaching 0, aren't they? However, when you look at the sums, we start out, we have 1, then it gets bigger, 3/2, then it gets a little bigger, 7/4. The next one should be a little bigger, shouldn't it? Is it possible for this to not overflow, for this to not become infinite? What do y'all think? Is it possible? Can we ever get convergence on this thing or not? Do you have any opinions? You don't think it's possible to get convergence? It will be 1 over a really big number at some point, yes, but that's still something, isn't it? See, this is where your logic starts to, your intuition may not be acting correctly here, because if you look at it in terms of like a real problem, what you're saying is, look, let's say we have a bucket. This bucket's finite. I'm going to first go in here, I'm going to throw like, 1 ounce of something in there, right? Then after that, I'm going to throw in, what? I should have done this, 1 ounce, right? And then I'm going to throw in 1/2 an ounce, and then I'm going to throw in 1/4 of an ounce, and then 1/8 of an ounce, and then 1/16 of an ounce. And no matter what, each time you do that, the water level comes up just a little bit, right? Because you're throwing something in there. I know we can talk about like atomic level and stuff. Just theoretically, if I'm putting something in, right, it must have some volume to it, so it's going to bring it up. So each time, and I never stop. How can this ever be finite? But each one is something. But it's still positive, right? It's greater than 0. But it's still something, right? So we could argue back and forth about this. You know, your argument is that they're getting small fast, too fast. And my argument is that it's still something. And you can't tell me you can't pile something on top of something and not eventually overfill. So you got this, do y'all see kind of the dilemma? There's good arguments both ways. It turns out, though, that this will not overfill, all right? It won't do it. It's going to be finite, all right? And what we need to do is be able to determine when that happens. Right now, we're not there yet, okay? We're not ready to handle that. Let me give you another example. How about this one? Sorry, comma. We won't have that formula yet. We're going to do it today. We just not yet. Just hold tight. Okay, recapping what just happened, right? Let's just recap what just happened. The first example I gave you, 1, 2, 3, 4, 5, we said when we started adding those up, it was obvious that that was going to overflow, right? That was just going to become infinite. Then I gave you the example 1 plus a half plus a fourth plus an eighth plus a 16th, and we saw that each one of those got smaller, and I told you that when you add those up, it's finite. So you may think now, okay, if they get smaller, then it's going to be finite. So what about this one? This gets smaller, right? Finite. Finite or infinite. So get your bucket out. Start filling this thing up. Overfill or not? Overfill, why? It's not getting small fast enough? Okay, so the argument on the previous one wasn't that they were getting small, it was that they were getting small fast enough? And these aren't getting, so how do I determine what's fast enough? Right? Like, how am I going to figure that out? Then it's going to be hard, right? Yeah, well, that's why we're here. This one is going to become infinite. This one will overfill the bucket. So unfortunately, it's not as simple as, oh, if these go to 0, it's finite. It's not that simple. I wish it was, but it's not. Okay, let's break back to what we were doing. Let me give you an example of a sequence that we're gonna come up with a formula for S sub n, which would be the nth partial sum. So example, if we're given a sub n equals 1 over 2 to the n, find a formula for the nth partial sum. Now let's not make this any harder than it has to be, okay? A sub n is 1/2, 1/4, 1/8, forever, right? That's what it is. Start plugging in n equals 1, then 2, then 3. My S sub n is simply just adding up all of these forever. All of what? The 1 over 2 to the n's. This is what I mean by give me a formula for S sub n. Everybody recognize that all we've done is taken the definition of the sequence and plugged it into the summation. That's all we've done. Put a summation in front of the sequence, we have a formula for the nth partial sum. Oh, hold on. Made a mistake. Pardon. My variable has changed. That's the infinite sum. Change this to k. We need to stop at n. I asked for the nth partial sum. Everyone see the change I made? The nth partial sum is the sum starting at, now I can't use n because I want to stop at n. So I'm using k, 1 over 2 to the k, stop at n. Everyone agree that's going to give me the first one plus the second plus the third all the way out to the nth one? Yes? Okay. That's your formula for S sub n. Now we start to get to some theorems. Was that a groan? I thought I heard a groan when I said theorem. Oh. So this is what we were just talking about. If your sequence heads to a number, L, it means when I take the limit, it goes to a number L, and that L is not 0, then the series diverges. The series must diverge. So going back to this, where was it? Here. A sub n was n, right? What does this converge to? Let n go to infinity here. What does it go to? Infinity. Is that going to 0? No. This theorem says that if your sequence goes to something other than 0, you're guaranteed that when you add up all those things forever, it diverges. What's that? You're not going to get a finite number. It's going to get infinite. Or it could not exist, but it diverges. Remember, divergence meant infinity or doesn't exist, like the limit doesn't exist, or the sum doesn't exist. I'm sorry? All you do is you just say, look, if it goes to a number L, right? If it goes to a number L, then what's happening is you're adding what would be close to L each time, right? Each time you go out, like each one of those is getting closer and closer to L. I'll give you a better example. The sequence A sub n equals n over n plus 1. If you write this sequence out, it's 1/2, 2/3, 3/4, 4/5, right? That's what it's doing. If I start adding these up, notice that when you take this limit, let n go to infinity here, what do you get as n goes to infinity here? You get 1, right? That's not 0. This should diverge. The reason being that each one of these is getting closer and closer to 1. So you're basically adding up what would be very, very close to 1 plus 1 plus 1 plus 1. How could that ever be finite if you just keep on adding a number really close to 1 up forever? Just stack 1 on top of 1 on top of 1 on top of 1. There's no ceiling to that. So the way you would prove it is you would assume that there is a ceiling and you would contradict yourself. That's how you would prove that. But I'm not going to prove the theorem. Okay, that's a nice theorem. However, let's be careful with this theorem. What it says is that if this limit is not 0, then it diverges. Does the theorem say that if the limit is 0, it converges? No. But that's not the case. All right? So what we call this we have a sheet that I'm about to give you. Actually, you know what? Let me hand this to you now. That's right. Yeah, I haven't shown you that it does, but I've told you that it doesn't work out that way. Okay, please take a look at this. Our goal in the next week and a half, is to be able to look at a series and know if it converges or diverges. A series, not a sequence. And in order to do this, I'm talking slowly because I'm waiting for those to get handed out, we are going to have to really investigate these things, and it's not going to be an easy thing to just take, like when we were looking at sequences, right, 8-1, if I wanted to talk about convergence or divergence, you let n go to infinity, and that was it. If that didn't work, you use squeeze theorem maybe. Now, there's going to be a whole slew of things that we're going to have to look at. Here is a table of a summary of all of the convergence and divergence tests for series. The one that's up here is the first one. It's called the nth term test. And what? These are the ones that we use. Yeah, these are the most common ones. There's other ones that are slight adaptations of these, but these are the ones that you'll see in every textbook. Okay, so the first test, the nth term test. Let's read this across. The test is called the nth term test. So when you're doing homework and you're asked to, or a test, and you're asked to show, does this converge or diverge, you have to write down, by the nth term test, blah, blah, blah. If that's the way you're going to test it and come to a conclusion, you have to convince the reader that you've applied the right test. So that will be something that you will be graded on. It's not whether or not you come up with the correct answer. It's, do you pick the right test? Do you apply the test properly? Do you draw your conclusions properly? This is for series, yes. And this will also be for power series. Sequences, you put this away. This is not used for sequences. Okay. So look, the nth term test is always the first test that you want to try, because it can automatically eliminate a lot of work. Nth term test, you use it on a series. Now notice they have the sigma notation there. They don't show you where n starts or stops, right? That's just standard sigma notation. It says, it will diverge if the limit as n goes to infinity of a sub n. So that's saying the sequence part of it. If that sequence part of it goes to something other than 0, you are done. It is over. It diverges. The series diverges. Done. What about the comments? It's inconclusive. The test is inconclusive if the limit of your sequence goes to 0. And that's because of what I showed you earlier. I said sometimes it fills up finite, sometimes it overfills when it goes to 0. All right, so let's do an example. How about this one? I want us to look at the sum k equals 1 to infinity of natural log 2 plus 1 over k. Notice I switched my index over to k instead of n. Is that okay with you? Anybody have any issues with that? All right, so what I'm going to do, since this is a series and I'm trying to find out what it adds up to be, is I'm going to start out by looking at the inside. This right here is my sequence, right? That's my sequence that I'm adding up. I'm going to call it a sub k instead of a sub n because I'm using k as an index. I would like to know what the limit as k goes to infinity of the natural log of 2 plus 1 over k is. That would have been a homework problem from 8-1. 1 over infinity is 0. 2 plus 0 is 2. So this is just natural log 2. Natural log 2 is not 0, right? The natural log of 2 is not 0. Since the natural log of 2 is not 0, it diverges. So I would say by the nth term test, the sum k equals 1 to infinity, natural log 2 plus 1 over k diverges. Just write it down. Yeah, just write it down. Because later on in other tests, you're going to be, to do a test on a series, you're actually going to be looking at a different series. And then you're going to be comparing them, and you need to be very clear on which series you're referring to. So it's just best to write them in, just so there's no confusion. Understand? You could have, if you wanted to, before you did this, right in here, you could have put nth term test. Right here, you could have underlined it and said, okay, that's letting you know what I'm about to do, right? So as you progress through this, you're going to have to get better with your notation. What's not acceptable is for you to just write a bunch of crap down and nobody be able to tell what test you're doing. That's not okay. This is part of being becoming good at writing math down, making it legible to anyone who reads it. Yeah, you want to be able to go back to it in a month and understand what you wrote. In a week and understand what you wrote. Or in a year, you know. Okay, well, you know what I'm saying. Next, at some other point in your life, you would be able to go back and look at it. Okay, so we need to start talking about the convergence, right? Like we haven't talked about the convergence of a series. We need to get some notation out of the way first before we can do that. So some notation. If S sub n is the partial sum that is S sub n equals sum k equals 1 to n of a sub n, right? That's the way we define the partial sum, a sub k. Right? S sub n to us by definition means you take the sum starting at k equals 1, you stop at n. Okay, if S sub n represents the partial sum, then the limit as n goes to infinity of S sub n is equal to capital S, just capital S, is the sum of the series. Where? It would be n. Yep. Because look at what's happening here. Remember, S sub n is a sequence, isn't it? S sub n is a sequence. It's S sub 1, S sub 2, S sub 3, right? And if we say S sub n, it stops, doesn't it? And that just gives us the list of partial sums. This is S sub 1 was A1. S sub 2 was A1 plus A2. S sub 3 was A1 plus A2 plus A3. S sub n is A1 plus A2 plus A3 all the way to AN, yes? If I want to know what this converges to, I let n go to infinity, don't I? Because this is a new sequence. If I want to know what it goes to, let n go to infinity. That's what I'm doing. Let n go to infinity. Whatever that limit is actually the sum of the series. It's the sum. If it adds up to something, then that's the answer. So we have to take a limit of the nth partial sum in order for us to find the sum of a series. Why, are you talking like big picture? Why are we doing this? Man, okay. Okay. Yeah, there's so many answers to this question. Let me try and think of one that. Okay, I'll just give you a real. I don't know if I want to go geometric or like a geometric example or. My pausing isn't because there's no application to it. It's because I'm trying to think of something that would be the most applicable thing. I tried to motivate this whole thing with the graphing, remember, and showing you how we can approximate functions with other functions. That was like my main motivation, to try and get you to believe that to get there we have to understand all this. But let me just try to give you something else. I don't think you're going to like this example, all right? Because I think, again, you could ask the question, why would I want to know that, okay? But okay, so what I'm doing is I'm starting with the triangle in the middle, and then I'm making another triangle, and then from there I'm making another triangle, and I'm making another triangle, and then keep doing that forever. What's the total area of all of these triangles? It's not the area of the black triangle, is it? Because you've got little gaps. What's that? But it can't be bigger. But it's got to be finite, right? It's got to be less than the sum of those black ones, or the black one. So that would require an infinite series. I mean, you would have to be able to add up an infinite number of things, right? Again, now, why would I ever need that? I get you. I understand that. But you can't do that without an infinite series. So when we're trying to take a function, like a complicated function, and we're trying to fit a polynomial to it, we try and fit a polynomial on top of it, and it doesn't fit. So we have to add another term into that approximate function to try and get it to match even better. And we keep doing that, and eventually we keep adding more and more, and we can lay it right on top of the other one. But then we have to understand if that's going to be a series, this plus this plus this, an infinite series, we need to know how these things behave. Sometimes they add up and they work, sometimes they don't. I hope that that's enough, man. I don't know. What I'll do is I'll try and come up with something that's a little more specific to your major. So what's your major? Okay, give me next class. I'll give you something. All right, I'll get it very specific. Not everybody come to me now with it. I'm a biology major. I'd like an example with that. Okay. All right. We have this definition here now, right? Or notation. Capital S is what happens when we take the n partial sum and let n go to infinity, right? If this limit exists, then that's the sum of our series. Okay, so more theorem stuff. This is more of a summary of what we have up to this point. We know these two things. If limit, or I'll use different notation. If a sub n does not go to 0, okay? If A sub n does not go to 0, then what can you tell me about S sub n? Yep, then S sub n diverges. If the series converges, okay, and this is a finite number, then A sub n has to go to 0. Now, we already talked about this. We already talked about this, right? I think I convinced you that that was true. I tried to a little bit. This one is a direct consequence of this one, and it requires that you understand the way logic works. All right, so let me try and explain a little bit of logic. This is not a logic class. But for those of you who've ever seen something like this, if P, then Q. Anyone ever seen that sort of logical structure? If P is true, then Q. If X is 2, then X squared is 4. If X is 2, then X squared is 4. Do you agree with that? Does it work the other way around? If X squared is 4, does that mean X was 2? It could be, but it's not guaranteed, right? It could have been -2, right? So our logical structure does not work that you can just flip the order of this. I'll give you another example. If you live in the U.S., the United States, if you live in the U.S., then, if you live in Texas, let's start with that. If you live in Texas, then you live in the U.S. Is that true? Does it work the other way around? If you live in the U.S., do you have to live in Texas? No, right? Now, but what is equivalent to if P then Q is the following statement. If not Q, then not P. These two statements are logically equivalent. If X is 2, then X squared is 4 is equivalent to me saying what? If X squared is not 4, then X could not have been 2. Or let's try the U.S. citizen one. If you are not living in the United States, then you are not living in Texas. That's true. So go back up to this. If you are not converging to 0, then you are diverging. What would the equivalent statement be? If you're not diverging, which would mean if you are converging, the series is converging, then you are not doing this. What's not going to 0? That's going to 0. So this theorem is just another version of this one written in what's called, and I haven't been proving theorems in so long, I believe it's called the contrapositive, or the contrapositive is when you flip it and do knots on each one.
So is it one or the other?
What do you mean?
Like your answer or something will always be one or the other?
Well, let's see what this is saying though. If it converges, then the sequence A sub n had to go to 0. Unfortunately for us, we are going to look at the sequence and try and get to know if this is true. The only thing we can say is this. I guarantee you, if the series converges, the sequence had to go to 0. That's guaranteed. But if the sequence goes to 0, that does not mean the series converges. So it does not go this direction. I don't know if that was addressing what you were asking, but.
So would that be like the 1 over 2, the 1 over 4, the 1 over 8, the 1 over 16? You know what I mean? Like that?
Yes, that series converged because I told you it did, right? And since it converged, well, the sequence had to go to 0. So I'll put in here, careful. We are not saying that if A sub n goes to 0, then S sub n converges. Okay? We are not saying this, everyone. Okay? We are not saying that. On a test, if you are trying to find whether or not a series converges, and you look at the sequence and you go, hey, that goes to 0, it converges, you will lose all the credit on that problem. Out of 10 points, you will lose 10. Because that is not what we're saying. If it goes to 2, though, it diverges and you're done. If it goes to 0, you move on to the next step. So I will hand you another sheet of paper. I'm not big on flowcharts, but I found this flowchart online, and I figured we'll give it a shot. I've never used this in this class. Yes. I haven't decided. I was asked if you're allowed to use that table of summary of all that stuff on the test. Okay, so look, everyone have this? Use it or don't use it as a study aid while you're doing homework or whatever. I think this gets a little bit involved, a little bit too much, in my opinion. But some people like things like this. It's a flow chart. Y'all know what a flow chart is? The first thing you do is start on the first top left. Test for divergence. Does the limit as n goes to infinity of a sub n equals 0? Yes or no? If no, it diverges. You're done. If yes, welcome to the rest of the flow chart. Okay? And then it becomes whatever. Okay? This is what I was saying. You cannot, this conclusion here would be you going down on that flow chart to the yes. And then there's a bunch of other stuff you have to look at. All right. Don't get too involved with that right now. Let's move on. All right. 3 important series. So there are some series that we really need to be able to be comfortable with. They are, the first one, what's called a geometric series. The next one is what's called a harmonic series. Next one is called a telescopic or collapsing series. I'll tell you all a quick little story. And don't take this the wrong way because of what you asked me just now, okay? Because you have a valid question. You want to know how this is used in like a real world application, right? Okay. I was in a math class called number theory when I was like I think I was a junior or senior, all right? So everyone in there was a math major at that point. And one of the guys sitting behind me, just in the middle of class, interrupted the professor. Now, this professor like never turned around. He was at the board the entire time. He just basically wrote down his notes, and you copied them, and then you went home and tried to make sense out of them. So he was writing, and no one really asked any questions. So we're just sitting there copying them, and about 4 or 5 weeks into class, this one student sitting behind me says, excuse me, you know, and then, you know, Dr. whatever his name was, I won't say who it was, turned around and was like kind of irritated. And the guy goes, why do we need to know any of this? Like, why do we need to know this? So the professor put his stuff down and pointed at the guy and told him to go outside, and they were gone for like half an hour. And then the professor came back, and that was it. The kid didn't come back. And so we found out later he took him right to the admissions office and dropped him. He walked him to the admissions office and dropped him. So because his idea was that if you're in a math class, you're a junior, senior level, that's not an appropriate question to ask. Why do we need to know this? Interesting, huh? Yeah.
That's all the way in there.
Yeah. So, yeah. Which I kind of understood as a student. I kind of understood that, like, because I wasn't asking questions either. It was just like I was learning stuff. I wasn't really asking like, why do I need to know this? I was more of asking. I mean, again, this is not to you because I think if I was a civil engineering major, why do I need to know about infinite series is a great question. If I'm a math major and I'm studying prime numbers and behaviors of prime numbers, I'm learning that because I chose to be a math major and I'm learning about prime numbers. Like that's why I'm there, right? Like it's very abstract, very abstract. So, okay, get back to this. There are three important series. Three important series. Geometric, harmonic, and telescopic. There's no way we're going to get through all of these today. The only one we'll probably be able to touch is geometric. So we're going to start with geometric series. Yes?
Does geometric mean anything? Because in movies, like when writers need jargon for the sciencey types, they're just like, oh, it's like, look at the thing. It's a geometric grade. Does that mean anything, or is that just?
I'm not sure in the context that you're talking about, but I know that in the movie Good Will Hunting. Oh no, that was a different quote. There's a Maclaurin series. He says Maclaurin series in that movie, which we'll study Maclaurin. I don't know. I'd have to see how it's being used. Geometric series is a classic series. I mean, it's a very well-known series. It behaves a certain way. It has to look a certain way. So what do they look like? What does a geometric series look like? Here it is. All geometric series have this form. A plus AR plus AR to the first power, squared, plus AR cubed plus AR to the fourth plus dot 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 forever, which I could rewrite using a sigma notation like this. See if you agree with that notation. Every one of these terms has an A in it, right? Then I have powers on R. The powers on R start coming up. But my first term doesn't have an R, so it's really like an R to the 0. So I need that when I plug in 1 for K, I get a 0 for the power. So I do K minus 1. Everyone see that? This is a geometric series. A here is a constant, and R is a constant. So these are just numbers. Would you like an example before we study it anymore? Like an example of a geometric series? 1 plus a half plus a fourth plus an eighth plus a 16th. Keep going forever. That is a geometric series. Because this is 1 plus 1 half to the first power plus 1 half squared plus 1 half cubed plus 1 half to the fourth plus dot dot dot. Do you agree with that? So what's A for us in this problem, in this geometric series? What's A? 1. It's 1 the whole time. It's the number sitting in front of all of these. 1, 1, 1, 1. And what's R for us? 1 half. Okay? That's a geometric series. Another geometric series. How about we do 3 plus 6 plus 8. Oh, wait, no. 12 plus 24 plus 48 plus dot dot dot. This one's a little harder to see. So I'll just kind of help you in case you need it. This is 3 times 3, 3 plus 3 times 2, plus 3 times 4, plus 3 times 8, plus 3 times what? 16, plus dot, dot, dot. Y'all see that?
Okay, so the initial number always going to be
Is the what?
the initial number that begins the series.
It could be, yes. Yes. Could be, because the series doesn't have to always start at A. It can be shifted around too. So we need to be comfortable with pattern recognition more than looking at it and saying, oh, it's always that number or something like that. We okay with that? What's A for us here? What's R for us? 2. Okay, now let's compare these two series. The first one was the one I gave you with we were filling it up, right? And I said it would not overfill. Yes? The other one, is it obvious that this is going to diverge? So I start adding these up forever. It's divergent. This one's convergent. This one's divergent. They're both geometric series. So the question becomes, in what case does a geometric series converge? In which case does it not? So when do geometric series converge is our question. When does a geometric series converge? Question. Okay, you ready? This is some cool stuff, I think. I want to know if this sum adds up to be something, right? That's what I want to know. If I take a geometric series, start adding them up forever, does it add up to be a number? So here's what I'd like for you to look at first. This is actually the proof of a geometric series and when it converges. See if you can follow this. S sub n, by definition, would be A plus AR squared plus AR cubed until I get to where? AR to the n, okay? That's the nth partial sum, right? I would like to know what happens to that when n goes to infinity. I started at, n minus, yes, thank you. Well, hold on. How did I write my formula? Okay, there's 2 versions, that's why. I did the k minus 1? Yes, then it's minus 1. You can start at n as 0. Sometimes, this is where the n equals 0 can come in. But that would be our formula. Do you all agree? All right, I want to know what happens to that when n goes to infinity. Yes? All right. I'm going to do something tricky here. Not a very natural thing that you would think to do. I'm going to multiply that sum up there by r. What's r times this? AR plus AR squared plus AR cubed plus AR to the 4th plus dot, 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 AR to the n. N minus 1, but then you're adding an r in there, so it'll be just AR to the n. Agreed? Now I'm going to do something even more unnatural. I'm going to take this sum, and I'm going to subtract this from it. Why? I don't know. Why? I'll tell you why. Because someone else a long time ago was trying to figure out what the hell this added up to be. And they beat themselves to death with it until they did this and it worked. That's what math people have to do. They have to try things that are totally unnatural until something happens. So what would happen if I take this line up here and I subtract this line down here? So imagine you're subtracting this line up here. Do you understand what I'm doing? That minus that is this. A minus, or all of this minus all of this. Do you see all the cancellation that happens here? This AR cancels AR squared, AR cubed, AR to the fourth. Okay. How about this AR to the n minus 1? Does it cancel? What's the one right in front of this one? Isn't the one right in front of this one AR to the n minus 1? Isn't it? Because this one's to the n, this one's the one before it's to the n minus 1, so that one goes away too. So what is the only thing that's left? A, and then minus AR to the n. A minus AR to the n. Y'all okay with that? You could pull an A out. Yep. Now keep in mind, everyone, I was interested in this to begin the problem, right? I highlighted S sub n. I wanted to know what happened to that when n went to infinity, right? And when I looked at this, if I let n go to infinity, I mean, I just get more and more terms. That's what happens. I'm trying to find out what it adds up to be. So I multiplied by r, y, I don't know, and then I subtracted y, I don't know. Well, look at this right here. Both on the left side of this equation, I have an S sub n, so I can factor it out. Agreed? And now I can divide both sides by 1 minus r. And check that out. I don't have an infinite sum anymore. Sorry, I don't even have a sum anymore. I'm not summing out, right? All I have, the only thing that's controlled by n here is this, right? Look, I mean, that's the only thing that has an n on it anymore. So let's now take a limit. I would like to know now, what is the limit as n goes to infinity of S sub n? Well, that's the limit as n goes to infinity of a minus a r to the n over 1 minus r. So you need to focus all your attention on this piece right here. Tell me what happens as n goes to infinity of r to the n. It depends on r, doesn't it? We did this last class. We said if r was less than 1, it went to 0, right? It went to 0. And if r was greater than 1 or 1, it diverged. So this limit is going to be one of two things. If the magnitude of r is less than 1 and the magnitude of r is greater than 1 or equal to 1. So tell me what happens if the magnitude of r is bigger than 1. It diverges, right? This thing diverges. The whole thing here will blow up. It'll get infinite. So diverges. What if the magnitude of r is less than 1? You said that this piece right here goes to what? 0 times a is 0. A minus 0 is a. A over 1 minus r is a over 1 minus r. That's our conclusion. The sum of a geometric series, an infinite sum of a geometric series, is one of these two cases. Okay, so let's go back and take a look at this example we just had. What was it? 1 plus a half plus a fourth plus an eighth plus a 16th, right? So I would like for us, if we could, to please write this in its appropriate notation, which would be 1 times 1/2 to the k minus 1. No, I'm just doing that to point out that we have the a and we have the r, right? That's the geometric series. Anyone have a question on how to get that sigma notation or where that sigma notation came from? Okay, So when we look at this, we say first, this is a geometric series. It is a geometric series. We identify that. Since it's a geometric series, the first thing I'm going to do is, or after that, I figure out it's geometric, is I'm going to say, okay, what's the magnitude of R? Well, the magnitude of R, in our case, is the magnitude of 1/2, which is definitely less than 1. Since it's less than 1, this geometric series converges. What does it converge to? This converges, right, because of this. What does it converge to? A over 1 minus R, right? Which is 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. So if you take a bucket that holds 2 liters and you pour in 1 liter, right? And then you follow that with 1/2 a liter, and then you follow that with 1/4 of a liter, and follow that with 1/8 of a liter, and you do that, repeating that pattern forever, you would get closer and closer and closer to filling up the 2-liter container, but you would never overfill it. And you would never reach 2 because you can't do that infinitely many times, can you? Now, there's a thing called Zeno's paradox, which talks about how you can never, no one can ever complete a race. Because let's say I have a race that I have to run a mile. I have to first run 1/2 a mile, right? Then I have to run 1/4 of a mile. Then I have to run 1/8 of a mile, and then 1/16 of a mile, and then, right? And I have to keep doing that. I have to run this infinite number of smaller intervals of distance, right? So I can never do that because I can never do it infinitely many times, right? Well, I mean, but we know you can finish a 1-mile race, right? So that's why it's called Zeno's paradox. It's like, well, you mathematically, theoretically, you have to do that infinitely many halves. So you can't ever do infinitely many halves, but you know that you actually get to the end of the race. So even though we know that if you add these up forever, you could never add them forever, they would converge to 2, we can just say that it is 2. The sum is 2. Okay, I still have 5 minutes. Find the sum. Notice that I'm actually asking you to find the sum. That's a critical hint to you. Because of all the series that we study, there are only 2 that we can find the sums of: geometric and telescopic. Those are the only 2. We've only looked at geometric. So on a test, if I say find the sum, I'm telling you that it's geometric or telescopic. We're not there yet. Yeah, we'll do that next class. Not going to have a whole lot of time to do this one. All right, because I'm down to 4 minutes, what we would do first, if we were starting this out, I'm told that it does add up, right? I'm told it converges. By saying find the sum, it's implied that it converges. Had this said, does this converge or diverge? If it converges, find the sum, then that would be different. So since it adds up, I'm thinking it's probably going to be geometric. Also, because geometric was like r to the k, wasn't it? K minus 1? And so this looks like that. It has a base and it has an exponent that has k in it. But the problem is I have it on the top and the bottom, don't I? So I'm going to try and make this look like this. So I'm going to try and make happen. So watch me make it happen in the next 3 minutes. I hope this looks familiar to you. See, in a geometric series, I need k minus 1, don't I? I have 3 to the k plus 1. I don't like that. I want k minus 1. So I can't just make it k minus 1, so I'm going to force it to happen. I'm going to write k minus 1 plus 1. But then I already had a plus 1 up there. And down here, I'm going to write 5 to the k minus 1 plus 1, but I already had a minus 2 down there. And the parts that I'm going to leave alone are these two pieces right here. And the rest of it, I'm just kind of put together. So watch. I have 3 to the k minus 1 times 3 to what power? 2. So what I'm doing is I'm saying, hey, I still had a 1 and a 1 here together. Add those up, that's 2. So 3 to the k minus 1 times 3 to the 2 is the same as this, which is the same as the original problem, right? I just have a clever way of rewriting it. And I'm doing the same thing down here. So let's see if you can help me get that in the next 30 seconds. 5 to the k minus 1, then what? Times 5 to the negative 1. Yeah, so this right here is all just a number, isn't it? 3 squared is 9. 5 to the negative 1, I can bring it up as a 5 on top. 9 times 5 is 45. So I have sum 45 times, now this right here, 3 to the k minus 1 over 5 to the k minus 1 can be rewritten as 3/5 to the k minus 1, can't it? Are we geometric now? We have sum k equals 1 to infinity. We have an a. We've identified a to be what? 45. We've identified r to be 3/5. Is that smaller than 1? Yes. I have k minus 1 up here. It matches the formula perfectly. This adds up to be 45a over 1 minus r, which is 3/5, whatever that is. A over 1 minus r. Look, I finished that all in time. Okay, let me give you your homework assignment. I have unfortunate news. Let me stop my video before I say this.